Risk Without Tears, an Overview by Ted G. Lewis, Ph.D. This overview surveys the basic elements of risk, including concepts of probability and consequence, and applies them to real-life situations. In simple terms, risk is a form of expected utility as it applies to the likelihood of loss. The elements of risk are the likelihood and the consequences of loss. Likelihood is measured in terms of probability, and consequence is measured in terms of lives, money, time, or opportunity. The units of risk depend on the units of loss. We'll first discuss probability. Probability is represented by a fraction between 0 and 1. This fraction can signify the likelihood or degree of uncertainty in any given situation. Its main purpose is to predict the future. We'll explore three fundamental methods of predicting the future. The first method is a priori, which means that we can predict the future by considering all possible combinations of what could happen, as opposed to what we think will happen. The second method is a posteriori, which means that we predict the future based on events from the past. This method assumes that the future will be like the past. The third and final method is conditional, which means that we can predict the future by knowing what actions leading up to an event have already happened. Risk is an application of expected utility theory. This theory has limitations, but it is the easiest and oldest method of predicting the future. According to Nassim Nicholas Taleb, our brains tend to go for superficial clues when it comes to risk and probability. These clues being largely determined by what emotions they elicit or the ease with which they come to mind. In other words, humans are notoriously poor at estimating risk. We're too emotional and irrational when it comes to quantifying risk. Humans are more psychologically vulnerable and behavioral animals than computers. Therefore, a disciplined approach is required to estimate true risk. This requires that we fully understand the elements of risk, probability, and consequence. To calculate risk, we must calculate the probability of an event X, the consequence of X, and multiply them together to get risk. A simple example will make this definition clear. Suppose you want to estimate the risk that a flood will damage your house. How is risk, expected loss, calculated? You need two numbers, the probability of a flood damaging your house and the consequences of flooding. Suppose you look up the probability of a flood in your neighborhood and find that it is 1 in 1,000 chance. Probability is 0.001. Further, suppose the damage to your flooded house is $400,000. Multiplying these together gives an answer. Risk is $400. What does this mean? It means that the expected loss, averaged over all possible outcomes, is $400. Why isn't loss $400,000? Because a loss of $400,000 once every 1,000 times a house is hit by a flood averages out to $400. Therefore, risk is the expected value of consequence, given that a flood happens only once in 1,000 trials. How should this number be interpreted? The foregoing information should make you feel uncomfortable, because the loss of a $400,000 house due to a flood is far from $400. Why the difference? The answer lies in how we interpret expected risk, which depends largely on how we interpret probability. This question has plagued scientists for over 350 years, ever since Blaise Pascal invented probability theory in 1654. There are three simple interpretations of probability that will help to explain the meaning of expected utility risk. The first interpretation is combinatorial. We tally all possible futures and focus on the one event of interest. This is called a priori probability because it is obtained before the event occurs. A simple example is the a priori probability of a coin turning up heads before it is tossed. If the coin is fair, the a priori probability is 1/2, or 50%. The second interpretation is historical. That is, we estimate the likelihood of a future event based on how often it has happened in the past. This is called an a posteriori probability because it is obtained after identical events have occurred in the past. The third interpretation is perhaps more interesting because it narrows down the possibilities through partial knowledge. If event A depends on event B, then the probability that A will occur is increased if B has already occurred. If B has not occurred, the likelihood of A is reduced. We can say that the probability of A happening is no longer independent. Rather, it is affected by B. Thus, probability of A is a conditional probability. Here's an example of a priori probability. Toss a coin twice and determine the probability of 2 heads turning up in a row. Step 1. Enumerate all possible future events. In this case, there are 4 possibilities: heads tails, tails heads, tails tails, and heads heads. Step 2. Count the number of future events that match what you were looking for. In this case, the outcome of interest is heads heads. Therefore, the a priori probability is 1 divided by 4, which is 0.25 or 25%. Gamblers like to quote the odds of winning instead of probability. Odds on is simply the ratio of success to failure. In probability terms, it's the ratio of the probability that an event will happen compared to the probability that the event will not happen. For example, in the previous example, 2 heads in a row occur with the probability of 0.25 and do not occur with the probability of 0.75. The ratio of these two is 1 to 3. Hence, the odds-on of obtaining 2 heads in 2 tosses is 1 to 3. A posteriori probability is based on historical observation. Suppose you visit a gambling table and count the number of times 2 heads turn up in 1,000 tosses of a pair of coins. Further, suppose that the count of heads is 273. Then the a posteriori probability that 2 heads will occur the next time a pair of coins is tossed is 0.273, or 27.3%. Why is this number different than the a priori estimate? There are several explanations. First, it is possible the coins are not entirely fair. They may be slightly biased or imbalanced in favor of heads. Second, probabilities are not certainties. They're estimates of the likelihood of an event over a large sample of events. In other words, the 1,000 tosses contain experimental error. If the coins are fair, the a priori and a posteriori estimates will converge as the number of tosses increases. This is known as regression to the mean. Other explanations include idiosyncrasies of the person tossing the coins, the surface where they land, and so on. The real world is a messy place. A posteriori probability is subject to error because of the law of large numbers. This law says that accuracy of a measurement, such as the probability of obtaining 2 heads in 2 coin tosses, increases with the number of times the pair of coins is tossed and the results are averaged. Another way of looking at the law of large numbers is to realize that an a posteriori estimate can be very inaccurate unless many samples are taken and averaged. The likelihood of another terrorist attack on New York City cannot be accurately estimated based on one attack. The likelihood of $1 billion of damage derived from a hurricane cannot be accurately estimated with only a handful of historical examples. The accuracy of measurements obtained from the averages of many samples is only improved if the process being measured is stationary. The thing to remember here is that accuracy depends on larger sample sizes. Steer clear of misleading smaller sample sizes. Keep within the parameters of a posteriori probability, and base your studies on samples taken from history. Remember the coin tossing example we used earlier? What is the probability of 2 heads in 2 tosses if we know for sure that the first toss produced a head? The fact that the first coin is known to be a head reduces uncertainty. This means the number of possible outcomes is also reduced, as you can see from the table. So the probability that 2 tosses turn up heads is conditionally 50%. We say the probability of getting a second head, given that the first toss is a head, is 50%. An event's probability is conditional if it is dependent on a prior event. Thomas Bayes developed an alternative interpretation of probability over 200 years ago, based on conditional probability. His idea is simple, but ingenious. What if we admit that probability is simply a measure of ignorance? The more we know, the less ignorant we are about the future. As more information accumulates, our ignorance or uncertainty decreases. By introducing conditional probability as evidence of some truth, we increase our degree of belief in the probability that a certain event will happen. Bayes reasoned as follows. All probability estimates are merely degrees of belief. Belief increases with evidence, and evidence is provided by conditional probability values coming true. His line of reasoning was boiled down into a theorem that simply says the conditional probability of event A, given that event B has occurred, equals the product of the probability of B and A happening together in the past times the ratio of probability A and probability B. Applying this theorem to the coin tossing example, note that we get the same result as before. The probability of getting a head and 2 heads in the past is 1.0, certainty. The ratio of getting 2 heads to getting 1 head is 0.25 divided by 0.5, or 50%. Bayes' theorem contains conditional probabilities as evidence. The term conditional probability of B given A is a posteriori evidence, historical data that increases our belief in the probability of A given B when the probability of B given A has been observed in the past. Thus, Bayesian probability is a belief system that increases or decreases the degree of belief in a particular likelihood, depending on evidence in the form of conditional probabilities. In summary, risk is an application of expected utility theory. When more than one type of event is possible, such as a flood and fire, the risk of both is the sum of individual risks. If the risk of a flood is $400 and the risk of a fire is $200, the overall risk is $600. The application of expected utility theory to risk assessment is simple to understand and apply, but it has its flaws. These shortcomings will be addressed in detail with subsequent presentations. Now for the answer to the question left unanswered earlier. Why does risk of $400 due to the likelihood of a flood damaging a $400,000 house make sense? Imagine a future in which 1,000 parallel universes exist. In all but one universe, your house is unscathed by floods. There is no damage whatsoever. But in one parallel universe, your $400,000 house is completely destroyed by a flood. In 999 parallel universes, 0 damage was done, for a total of 999 multiplied by 0, which of course equals 0. In one parallel universe, $400,000 in damages was done, for a total of 1 multiplied by $400,000. Expected utility theory is exactly what it says, expected value of consequence. Risk is applied expected utility theory. It depends on faithful estimates of likelihood. While we cannot predict the future, we can estimate its likelihood. There are 3 methods available to us. A priori probability is based on mathematics. Simply divide the number of favorable outcomes by all possible outcomes. A posteriori probability is based on history. Simply tally what has happened in the past and use the past to predict the likelihood of future events. Bayes' theorem is the 3rd method. Instead of estimating likelihood directly, Bayesian probability is really a belief system. Using conditional probabilities as evidence of future events, degree of belief in these future events is estimated by applying Bayes' theorem of conditional probabilities.